let's start.
Oh, sure. Hi, everyone. Happy New Year. Welcome to the first session of online seminar on the math foundations of data science in the year 2021. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great honor to introduce our distinguished speaker, Professor Yuejie from CMU. Professor Chi is an associate professor in the Department of Electrical and Computer Engineering at CMU, where she holds a Robert E. Doherty Career Development Professorship. She is also an affiliated faculty member with the Machine Learning Department and SciLab. She has made fundamental contributions to the theoretical and algorithmic foundations of data science, signal processing, machine learning, and inverse problems. She has received many prestigious awards, such as the Presidential Early Career Award for Scientists and Engineers from the White House, and NSF Career Award, Young Investigator Awards from Air Force Office of Scientific Research, and Office of Naval Research, and Google Faculty Research Award, IEEE Signal Processing Society Young Author Best Paper Award, among others. In 2019, she received the inaugural IEEE Signal Processing Society Early Career Technical Achievement Award. The title of Professor Chi's talk today is Preconditioning Helps Faster Convergence in Statistical and Reinforcement Learning. And please join me in welcoming her.
Thank you, Jordan, for the very kind introduction. It's a great pleasure for me to being able to give this talk during this difficult time. I hope everyone is having a staying safe and happy New Year. Hope 2021 will treat us better than 2020. Okay, so today I'm going to talk about some of our recent work in understanding preconditioned first order methods in solving some statistical and reinforcement learning problems. Okay, many of the problems we are dealing today in data science, machine learning, signal processing can be solved as optimization problems, where we're given some data and model and try to estimate some parameter of interest by optimizing some function of x. And typically, in many applications, this leads to a non-convex problem. In general, this can include problems such as training neural networks or simpler classical problems such as dimensionality reduction using principal component analysis, for example. Okay. Now, the traditional view of non-convex problems from optimization theory is that this problem tend to be very hard to argue about global optimality. Indeed, even for very simple problems such as training one-layer neural network, you can find configuration of the data where the landscape can be bumpy everywhere, where you have exponentially many bad local minima. Okay. With this kind of understanding in mind, indeed, quoting a famous saying by Rockefeller, people think of the great watershed between in optimization isn't between linearity and nonlinearity, but between convexity and non-convexity. Right, so how can we deal with non-convex problem in a provably efficient fashion? What comes to save this in today is that statistical models often come to rescue. Indeed, by proposing and recognizing proper statistical models of data, one can often translate a worst-case scenario into a much more benign landscape picture. If we think about the average case performance of the problem, just think about the average realization of the data and what kind of landscape we may typically obtain, the problem can become much more simpler, so that even very simple algorithms such as gradient descent or alternating minimization can be efficient for non-convex learning. Particularly, in today's talk, we'll be focusing on first order methods due to their efficiency in terms of scalability and also maintainability for some computational advances such as parallelization. As vanilla gradient descent, for example, this is what people typically use. It's very popular in practice, where you just simply update your parameter along the descent direction of your loss function. Right. Indeed, this line of thinking has been quite successful in the recent literature for the probably maybe last 10 or 20 years. There has been long research for coming up proven efficient non-convex optimization procedures for dealing with some challenging non-convex problems, such as phase retrieval, matrix completion, dictionary learning, and some deep learning problems. All right. Now, in today's talk, we're trying to move one step further along this line of thinking. Particularly, we'll be focusing on addressing the computation efficiency of vanilla gradient descent. Okay. Indeed, even from the classical literature of convex optimization, we know vanilla gradients tend to be computationally inefficient when the problem is yield conditioned. Okay, so you often have to use much smaller step size and suffer a price in terms of condition number of your loss function in terms of computation efficiency when you use vanilla gradient descent. What we are going to try to promote, hopefully after the end of the by the end of the talk, is this idea of preconditioning. Often, if you can explain the structure of the problem, you can maybe come up with very cheap and computationally efficient design of preconditioners, such that by using a preconditioned variant of gradient descent, you can actually accelerate the convergence of the problem without paying too much in computation. Okay. With this slogan, I'm going to try to convey, talk about two recent case studies done in my group. The first is on the problem low rank matrix estimation in the scope of statistical learning. And the other is about policy optimization in the scope of reinforcement learning. Okay. So for the first problem, this is going to be dealing with how to accelerate the estimation of your condition low rank matrices. This is joint work with my student Tian at CMU and also Chong Ma, who is currently a postdoc at Berkeley, but he'll be soon joining the University of Chicago as assistant professor in statistics. All right. So low-rank matrices are a ubiquitous object in many applications in science and engineering, ranging from applications such as radar imaging, hyperspectral imaging, to problems in data analytics for dealing with recommendation systems and bioinformatics. Roughly speaking, you can think of low-rank matrices as a redundant representation of a small number of latent factors that you are interested in extracting. Okay. Mathematically, we'll be dealing with this canonical problem low-rank matrix sensing in this talk, where we have some ground truth matrix, say M, which is a high-dimensional matrix N1 by N2, whose rank R is much smaller than the ambient dimension of this matrix. And we're going to collect measurements of this low-rank matrix using some sensing device or data collection scheme, which is modeled as a linear map A. And we're collecting a bunch of measurements we call Y of dimension small m. Possibly the measurements can be corrupted by noise. And the particular interest, often we are interested in solving this problem in the so-called sample starved regime, where the number of measurements M, our sensing budget, is much smaller than the ambient dimension of the low-rank matrix, but just barely larger than the degrees of freedom of this matrix if you capitalize on its low-rank structure. All right. So one natural way to think about solving this problem is simply just to try to find a matrix of rank R such that the observation residue is minimized using the natural least square laws. Right. However, this formulation has two issues. One is that the rank constraint often leads to some NP hardness in the problem. Second, this is operating in the ambient dimension domain, that the matrix can be potentially very large, so that it may be computationally not efficient. To deal with this issue, a popular strategy is to invoke the matrix factorization by rewriting this matrix C as two tau matrices, product of two tau matrices X and Y, each of them only contain R columns. And with this, we can reformulate the loss function into one that's with respect to the factors in this way, right? So basically, the benefit of doing so is now we are optimizing over much smaller matrix factors X and Y, so while saving memory computation. But on the other end, this formulation inevitably introduces non-convexity into the problem, so it's much harder to argue about its global optimality in general. Right. So how to deal with this? From the line of research I just mentioned earlier in the introduction, one way to solve this problem is actually using gradient descent, by optimizing a carefully designed loss function where they introduce another balancing regularization, which is roughly just balancing the norm of the factor matrices X and Y. And this sort of convert this landscape, which is still non-convex, but into a sort of better structured one, where theoretically you see there is this so-called sort of local basin of attraction that look like a strongly convex function around the global optimal. And this motivates this very popular approach, which is a two-step approach where you first start by trying to find a smart initialization, often done by the spectrum method, so that it can lens into this basin of attraction. Once you find this nice initialization, you can run some simple local search heuristics such as gradient descent to converge quickly to the ground truth. Okay, in this presentation, I'll be mostly focusing on the local refinement stage, but we'll ask you to trust me that the spectrum method indeed is a very powerful method to come up with good initialization. And as a shameless plug here, we actually recently did a monograph just on spectrum method alone for its applications in data science. So if you're interested, you can find the monograph on arXiv. All right, and this method is indeed quite successful. And quoting a prior theory on this method, if we know the ground truth matrix is exactly low rank and has a condition number kappa, which is the ratio between the largest non-zero singular value and the smallest one, then if you're solving this low rank matrix sensing problem with IID Gaussian design, we actually know vanilla gradient descent reach epsilon accuracy with a number iteration which is on the order of kappa times log 1 over epsilon. This is nice because it achieves this so-called linear convergence with respect to the accuracy level you want to achieve at a statistical complexity which is slightly larger than the degrees of freedom of the problem. So this is basically saying that this vanilla gradient descent approach achieves both statistical and computational guarantee in a pretty efficient fashion. Okay, and indeed, similar results has been shown for many other low-rank problems such as matrix completion, phase retrieval in the literature by a long line of research that works that I won't have time to get into. Now, what we would like to be focusing on today is a computational aspect of this approach, particularly when the condition number of the underlying low-rank matrix may become large. So on this slide, I'm showing you a simple toy example of matrix completion where I'm fixing all the parameters except the condition number of the low-rank matrix. And you can see that clearly the iteration complexity grows quite fast when we increase the condition number, even to sort of a relatively small scale. So basically by increasing the condition number, say by 10-fold, the computational complexity is also increased roughly by 10-fold. Right? So this is indeed quite consistent with what the theory is saying, so that this scaling up, linear scaling with respect to the condition number is not an artifact. It really happens in practice when you run this vanilla gradient descent algorithm for solving such factored matrix estimation problems. Okay, now why do we want to care about the condition number? In practice, when we are dealing with real data, condition number can often be pretty large. I want to illustrate this just using a real data example, which is a quite simple one, but also quite representative. So this is a real data about coloring concentration levels at water junctions, which is measured at different times. So I'm looking at a particular data that is measuring chlorine concentration level at 120 junction at 180 times loss. So this gives me a basically matrix of 120 times 180. And if I plot the singular values of this matrix, this gives me this very nice power law decay, where the singular value decays pretty fast as I increase the index, right? So this is really suggesting this matrix can be well approximated by a low rank matrix. Indeed, if I want to approximate this matrix as a rank 5 matrix, which captures about 88% of the total energy of this matrix, this gives me a condition number about 20, right? Now, if I want to increase a little bit about the rank approximation to a rank 10 approximation, which captures a little bit more energy, about 96%, the condition number becomes even larger at around 60, right? So this indeed is suggesting the condition number often is non-negligible when we are dealing with real data, even with a small rank approximation. So this leads to the natural question about can we actually try to accelerate the convergence of gradient descent to an iteration complex that is independent with the condition number. For people who are familiar with this literature, we know that there are actually other type of algorithms, such as alternating minimization or singular value projection, that can indeed achieve such a condition number independent rate. However, the per iteration cost of those problems tend to be much more expensive and often has implicit dependencies with the condition number. On the other hand, we want to focus on gradient descent or first order methods in general, because this type of methods in general has better scalability and can be potentially adapted to in conjunction with some system advantages. So that's why we want to focus on specifically on how to accelerate the convergence of gradient descent type of methods in this particular work. Okay. So the answer is indeed yes. Otherwise, I won't be giving this talk. In our paper, we have developed this new algorithm that we call the scaled gradient descent method. This method, again, is a two-step approach that starts with spectral initialization, which is the same method that I used in the previous one. But we are only going to change the way we do the local refinements. And there are two key changes we are introducing. So the first one is we actually do not need the balancing regularization. We can operate this method directly in the vanilla laws, the naturally square laws, without the balancing regularizer. Balancing regularizer is actually something people know it is not necessary when you use spectral initialization, but it's just convenient for theory. Now, when we use scale gradient descent, we can actually show this indeed is not necessary. Another thing we did, which is more critical for the success, is that instead of using the vanilla gradient as a search direction, we actually also introduced these preconditional matrices, where you see the search direction of the left factor matrix X is preconditioned by the inverse of Y transpose Y, where Y is a right factor matrix. Similarly, you are preconditioning the right factor using the inverse of X transpose X, where X is a left factor matrix. So these matrices are actually only R by R. So the cost of computing these preconditioners is relatively cheap because the rank is typically much smaller than the ambient dimension. So this only adds a minimum computational overhead to the computation of the gradient, the search direction. So with this being said, as a one-line quick summary of what this method is, you can essentially think of scale gradient descent as a preconditioned gradient method, first order method, without introducing the balancing regularization. All right. Now, this change seems to be quite simple and straightforward. Does it really work? Surprisingly, it works really, really well in the sense, coming back to the same earlier example I have, we can see if by benchmarking scale gradient descent with vanilla gradient descent, indeed, scale gradient descent achieves the same performance as vanilla gradient descent when the condition number equals 1, which is a perfect conditioning case. And as you increase the condition number, the performance of scale gradient descent is actually unchanged. It gives you the same complex iteration complexity, regardless of the condition number. So indeed, it achieves a condition rate that is kappa independent with a minimum computational overhead. Okay, so with this nice encouraging empirical observation, we want to be able to justify this theoretically. And before I do that, just want to show a little bit of underlying designing principles about why this method might actually work. So one of the first key property of this method is that it is actually introduced, the introduction of the precondition brings out a nice invariance property of the trajectory of the algorithm on the low rank matrix manifold with respect to invertible transforms. We actually first did this method independently and later figured out there were actually some precursors literature especially in the Riemannian manifold literature, where people motivate similar kind of preconditioner, but solving this problem on the low rank matrix manifold. So what this is really trying to say is that, remember that this low rank matrix factorization is actually not unique up to invertible matrix factorizations. So if you change the parameterization of these low rank matrix factors, the trajectory of, you may get a different trajectory or algorithm when you're running the vanilla gradient descent. But with the scaled GD algorithm, if you think about the trajectory along the low rank matrix manifold by taking the product of low rank factors, you always get the same trajectory. So the trajectory of the algorithm is actually equivalent with respect to the change of the invertible transform, which is really the key. Okay. Now, another key thing we have to do in the analysis is to figure out the right distance metric or Lyapunov function to track the progress of the algorithm. And particularly, we have to carefully change the way we measure the distance between the current iterates to the ground truth factor by carefully injecting the sort of the impact of the preconditioners in this distance. And we are also dealing with invertible transforms in this distance metrics. Well, if you add balancing regularization, you only need to deal with also normal transforms rather than invertible transforms, which is easier. So with this new distance metric, together with a bunch of algebraic tools to analyze this distance metric and a careful trajectory-based analysis, we finally were able to arrive at this theorem, which is basically the following. This is something that you can benchmark with the result I showed you earlier by Tu et al. Essentially, for the same low rank matrix sensing problem with IID Gaussian design, this algorithm achieved epsilon accuracy, now probably at the iteration complexity that is independent with the condition number, only on the order log 1 over epsilon. And the sample complexity is still the same as the previous 2AL algorithm. So really what this is saying is you can achieve strict improvement over the previous result using vanilla gradient descent by using the scale gradient descent algorithm. Particularly in the computational efficiency, where the iteration complexity is being probably accelerated by a factor of kappa at the same sample complexity. Okay. Now, indeed, our discovery of this preconditioner or this line of theoretical thinking in terms of is actually quite general. You can apply the same type of preconditioning to accelerate problems such as robust PCA, and where the goal is try to decompose a matrix into a low rank component and a sparse component, and the matrix completion problem, where in both problems we can basically accelerate the computational complexity by a factor of the condition number at comparable sample complexity requirements. So all in all, this method gives us a huge computational saving at comparable sample complexities, particularly for estimation of low yield condition low rank matrices. Okay. Now, one thing I want to just mention briefly is about the numerical stability when you have noise or imperfect rank information. Indeed, the key message here is if you, for the same, just illustrate this using a small data example, the same chlorine concentration level data set, the message I want to convey here is that scale gradient descent is not giving you a better solution. Okay, we're not claiming we can give a better solution to vanilla gradient descent, but rather we're claiming scale gradient descent achieves the same accuracy at a much faster rate in terms of computation. So in this figure, we show the performance of scaled GD and vanilla GD in about 400 iterations, where you see scaled GD already achieve a very good recovery accuracy around, say, 100 iteration. While vanilla GD will have a very long tail that converge much slower. But if you give vanilla GD enough time, say, if you run this algorithm to thousands of iterations, vanilla GD will actually also eventually arrive at the same solution, but just at a much higher computational cost. Okay, so this method also can be generalized to the scenario where you have corruptive measurements. So this can often happen in practice when you have sensor failures or have malicious attacks, where your observations can be potentially corrupted by an additional term, which is modeled as a sparse vector, where the location of the non-zero entries corresponding to the corrupted entries. And typically, the amount of corruption can be thought as small. Say, for example, 5% of your total observation can be corrupted in an arbitrary way. When this happens, the least square loss often is not your right bet, but rather you may want to use another loss function which is more robust to outliers, called the least absolute deviation of loss, which simply replaces the squared L2 loss by the L1 loss. Okay, by doing so, you introduce another sort of challenge into the optimization, which is the non-smoothness of this loss function. But still, it turns out that the scaled gradient can still be very helpful, where now all you need to do is to just precondition the subgradient of your loss function using the same preconditioner design as earlier. One thing you need to modify also when you deal with the subgradient method is the choice of the step size. You cannot use a constant step size anymore. Possible step size including using a polyak step size or geometrically decaying step size. With this in place, you can actually also show similar acceleration in terms of computational complexity than some previous methods that does not have this preconditioners. Essentially, you can again accelerate the convergence by a factor of the condition number for canonical problems such as matrix sensing and quadratic sampling. Okay, so because of time, I won't be able to get into the detail of this robust approach, but just want to summarize that by using this non-smooth loss, you can indeed achieve the best of both worlds, in the sense you now have robustness to both the yield conditioning of your low rank matrices as well as adversarial corruptions in your measurement process. Okay. All right. So with that, that concludes my first case study, which is focused on using the idea of preconditioning in accelerating low rank matrix estimation. Now I want to move into the second aspect of this talk, which is focusing on accelerating the convergence of policy optimization in reinforcement learning. This is joint work with my student Shicong at CMU, Chen Cheng at Stanford, and Yuxin Chen at Princeton University, and my colleague Yuting Wei, who is a faculty in the statistics department at CMU. All right. So reinforcement learning is another learning paradigm, which is a sequential learning paradigm. In reinforcement learning, an agent tries to basically learn by interacting with the environment, which is typically unknown. And the reinforcement learning has been hitting the news a lot recently, kept achieving superhuman performance in many problems such as gameplay, motor control, and so on. In reinforcement learning, again, optimization, particularly policy optimization, plays a critical role in driving these successes, which is something I would like to get into a little bit in today's presentation. To deal with reinforcement learning, we had to first get our hands dirty in notations in learning a bunch of mathematical models. Particularly Markov decision process is one prototype model for dealing with reinforcement learning, where we have an agent interacting with the environment in a closed loop. And the environment is modeled by a finite state space called S. For example, you can imagine this could be the current stone configuration in a Go game. And the agent will be making actions based on the state. For example, the action could be where to push the next stone in the Go game. And after the actions of environment will sort of reward the agent by a reward function which is a function of the current state and the current action. In this talk, we're going to think of this as a normalized scalar between 0 and 1. Okay, and what the agent is going to basically do is it tries to design this policy, okay, which is a probability distribution over the action space, condition on the current state, which is sometimes also called action selection rule. Okay, and the environment is modeled by this probability transition kernel, which basically tells what the next state should be, condition on the current state and action. So this is essentially a probability distribution over the state space when you condition on the current state and current action. Okay. Now, important quantity in reinforcement learning are these value functions and Q functions, which is essentially try to capture the quality of a policy that the agent is executing. Okay, so imagine that you are starting at certain initial state, and the agent tries to unroll a trajectory by executing a policy pi, and then you can evaluate the policy essentially by the total reward it is accumulating. Typically in a discounted setting, you'll be looking at the discounted total reward, where the future reward is discounted by a factor of gamma when you move one time step further. So basically, you can think of this parameter gamma as something between 0 and 1. If it is very close to 1, you are dealing with a long horizon problem where future rewards is almost equally important to you as immediate reward. In the literature, people often think about the factor 1 over 1 minus gamma as a so-called effective horizon, which is roughly the time horizon you care about the problem. Okay, so the value function is essentially defined by thinking about all the actions as taken with respect to the policy pi. Now the Q function is defined a little bit different, where only except the first, you want to take the first action arbitrarily, and then for the ensuing actions, you are taking them with respect to the policy pi. So by doing that, your Q function is defined as a function of the initial state, the state S, and also the first initial action A. Okay, so value function is a function of only the state, but the Q function is a function of the state and the action. Okay, and all these are sort of random, has randomness in it due to the randomness of the MDP and also randomness of the policy. So we are taking the expectation with respect to the sample trajectory under the policy and the randomness of the MDP when defining this value function and Q functions. Okay, so now we have a mean to evaluate the sort of the quality of the policy using these value functions. And now we can sort of and now before I go there, I want to just introduce another key thing that we're dealing with in today's talk, which is this entropy regularized version of these RL problems. So entropy regularization is kind of an old concept, first proposed by Williams and Peng in 1991, but kind of have been revived in the recent deep reinforcement learning literature because it sort of improves the performance empirically. Roughly speaking, what this entropy regularization trying to do is try to encourage exploration of the policy, especially when the state space is large. So what we are going to do is that still think about the same sort of trajectory you are trying to unrolling by performing with respect to a policy pi. But when you define your value function, instead of using that just the reward alone, you also want to take into the account of the stochasticity of the policy you're using. So that you want to penalize policies that are maybe too deterministic. So that gives you this actual term with respect to the log policies. And you can sort of control how much you want to penalize or promote the stochasticity of the policy by controlling the entropy regularization parameter tau. Okay. So basically what this does is now, instead of using the vanilla value functions that only look at the reward I'm collecting, I'm actually looking at this soft value function, but that also taken into consideration of the stochasticity of the policy that I'm executing. And this is sometimes called the soft value function in the literature. And in this particular talk, we'll be mostly focusing on this entropy regularized version of the problem. And the goal is try to find the optimal policy for this entropy regularized RL problems so that this soft value function is maximized under this policy. Okay. All right. So now I have sort of defined what the problem is, how to solve them using optimization methods. First, I need to get a sort of objective function. One way to do this is to sort of define a distribution over the initial state distribution, and then just aggregate this value function by averaging this over the initial state distribution rho, and this sort of give me this scalar objective function of the value function, which is a function of the initial distribution rho. And in order to deal with the fact that this policy lies on the probability simplex, I'm going to use this popular softmax parameterization that convert this policy into an unconstrained parameter theta that has the same dimension that is a product of the state space and the action space. Okay, so with this, I can finally have sort of unconstrained optimization problem where the goal is to sort of find the parameter theta that maximizes this value function parameterized by theta. All right. Okay, so policy optimization or policy gradient methods is nothing but try to execute a first order vanilla gradient descent method or gradient ascent method on it by just update the parameter along the gradient direction of your value function. We're using some learning rate eta to control how much you want to progress at each step. Okay. Now, there is also very important variant of this sort of first order methods that use a preconditioning idea that is called a natural policy gradient. This is a method first introduced by Kakade in 2002 in the context of reinforcement learning, where all it does is that instead of just search along the direction, which is a gradient of your value function, you want to search on a preconditioned direction where it is preconditioned by sort of the so-called Fisher information matrix. That depends on the parameterization of your policy. So what this tries to do is tries to sort of also introduce some invariant property to your search with respect to the different parameterization of your policy. Okay. Okay. So just to show a toy example that why this natural gradient descent can potentially help, I'm showing you a toy example, which is simple bandit problem with only 3 arms having a reward 1, 0.9, and 0.1, so that the first arm is sort of the optimal one. And I'm running both policy gradient and natural policy gradient for this toy problem, just assuming exact gradient, assuming I know the model exactly. So so this blue curves shows the policy gradient flow or the natural policy gradient flow from initialization point to the global optimal point. So immediately we see that first of all, both of these algorithms are actually converging to the global optimal, but the natural policy gradient is following a more direct path to the optimal policy. So it's being more computationally efficient compared to the ones that are using policy gradient. Okay. So this is indeed exactly the message we want to understand, right? Why? Okay, indeed, these policy gradient methods are quite effective and popular in practice because unlike some other methods, such as value-based methods, policy gradient methods tries to directly optimize a policy, which is our quantity of interest. And it also allows flexible differentiable parameterizations of the policy using, for example, deep neural networks. And it works with both continuous and discrete problems. And indeed, this variant of natural descent, together with a line search procedure, is essentially what is done in a very popular method called trust region policy optimization in the literature. So what we are trying to do, what motivated our work is, can we actually justify this efficacy of natural policy gradients, especially for the entropy regularized variant of reinforcement learning. Okay, so one of the challenge, again, theoretically speaking, is due to the non-convexity of the problem. Nonetheless, there has been a very encouraging recent line of work in the literature that people tries to understand the global convergence guarantees of these policy gradient methods for some of the sort of control problems such as linear quadratic regulators. And there are also literature understanding the unregularized policy gradient methods for tabular MDPs and unregularized MPG methods for tabular MDPs. So and there's a lot of many other works that are quite recently in the literature in the last 1 or 2 years that I don't have the space to cover. But this works all has been very inspiring to us and motivated our study. Okay, so in particularly, our work is focused on this variant of entropy regularized MPG, again, in this tabular setting of MDP. Now, in the tabular setting, turns out you can write down the update of the entropy regularized MPG algorithm in a very simple one-line way, directly with respect to the policy. Roughly speaking, the policy is being updated with this sort of multiplicative combination of the current policy, pi t, and a soft gradient version of the evaluation of the current policy in this sort of combination. So pictorially, imagine you are at some policy, say pi 0, and you want to look at how good this policy is by evaluating its Q function, okay? And you can come to another policy by sort of gradify it. If you take just the max of for every fixed state, you're doing a sort of stringent gradification. But in this entropy regularized version, you are doing this soft version by just taking the exponential map with respect to this second term here in the update. And then you are going to start taking sort of this multiplicative combination between the previous policy and this soft gradification, where the amount that you want to follow the soft gradification is determined by your step size eta. Okay, so eta is a parameter between 0 and 1 minus gamma divided by tau. And if you set the step size to the largest possible, you are essentially dropping the influence of the current policy and following directly the soft gradification as your update. Okay, so this actually gives this so-called algorithm called soft policy iteration that is quite popular in practice, especially in combination with actor critique. Another sort of interesting aspect of this update rule is that if you recall, we actually introduced policy gradient by introducing initial state distribution rule. But in fact, in this tabular setting for this MPG, the update rule is actually invariant with your choice of rule. Okay, so it actually didn't show up in this update. Okay, so with this, now I can actually talk about the convergence result for this update rule. We're going to first look at the exact scenario where we are assuming direct access to the model so that you can perfectly evaluate the Q function via current policy. Okay, and later we'll generalize this to an inexact case when you only have imperfect Q function evaluation. Our result basically says that for the entire range of learning rate, this entropy regularized MPG algorithm actually achieves linear convergence of the soft Q function to the optimal soft Q function at a linear rate, where basically the rate is sort of determined by both the step size and the sort of entropy regularization parameter, which I'll go into talk a little bit more later. But one thing I want to highlight is this result is actually very clear. There is no hidden constant. There's no excessively large consistent. Everything is spelled out sort of in a very clear manner that I personally feel is very hard to improve. Okay. Another thing is that with entropy regularization, your optimal policy also becomes unique. So you can also guarantee that you're going to converge linearly to the log policies, also at the same rate as earlier, except that the right-hand side now actually has an additional factor of 1 over tau. Okay. Now, what are the implications here? Basically, as we said earlier, you are achieving linear rate of convergence, and particularly focusing on the Q function to reach entry-wise accuracy up to the accuracy level epsilon. If you're using a general learning rate, your iteration complexity roughly scales on the order 1 over eta tau. So basically, if you're fixing tau as a small parameter, this is roughly saying if you increase the entropy regularization tau, you are going to converge faster. If you set the step size to the largest possible at 1 over 1 minus gamma divided by tau, then your convergence rate or iteration complexity, ignoring the logarithmic factor, is essentially 1 over 1 minus gamma, which is the effective horizon Mel problem. Okay, so more importantly, this also says that this entropy regularized MPG algorithm achieves this global linear convergence at a rate that is actually almost independent with respect to the dimension of your state space and your action space, which can potentially be huge, okay, despite the non-convexity of the problem. All right, so now it may be worthwhile to compare with similar results in the literature for this entropy regularized problems, but without using the natural policy, but just this vanilla policy gradient. So there's a recent work in this, or I should say last year's ICML, where they show this convergence result for vanilla policy gradient descent with entropy regularization. This result also appears to be in the form of a linear convergence with respect to the iteration count. However, you can see immediately this convergence is much more complicated, and particularly without deciphering all the terms, there is a term that is sort of depending on the minimum entries of your policy throughout the trajectory. And this term has unclear dependencies with respect to all the dimension of your state space and action space. And potentially this can be large and even potentially exponential with your state space, so that policy gradient can be computationally much less efficient compared with natural policy gradient descent, which is also kind of already illustrated in our toy example with on the 3-arm banded one. Okay, so with this, again, just to highlight, this entropy regularized MPG methods achieve a dimension-free rate compared to the one that is just using the vanilla policy gradient. Okay, as a side, it's also instrumental to compare with the vanilla MPG method without entropy regularization. Indeed, this feature of being dimension-free with respect to the state and action space is not new. Inspiring earlier work by Agavo et al. Actually already illustrated this for vanilla policy grid, for vanilla MPG method without entropy regularization. However, it is interesting to see that the convergence rate without entropy regularization is only sublinear, that converge at a rate of 1/epsilon. Well, even with a small amount of regularization, albeit it is important to emphasize that the regularization actually changed the global optimization, the global optimizer of the problem. But nonetheless, with entropy regularization, we can actually achieve a linear rate of convergence. Therefore, implying the fact that entropy regularization actually enables faster convergence compared with the unregularized counterpart. Okay, so now let me just say briefly about the scenario where you have only inexact evaluation of the policies. We consider the scenario where you have sort of black box estimator for the Q function that as long as your black box achieves the accuracy up to some accuracy delta, and you're going to sort of inject this estimated Q function into your entropy regularization update. Okay, and the question is how robust is this entropy regularized MGP method with respect to the inexact policy evaluation? Okay, so our theorem basically says that it is still robust as long as your policy evaluation is sort of reasonably accurate. So we show that basically the accuracy level of your policy evaluation delta needs to satisfy this bound, which is sort of proportional to the final accuracy epsilon, where we also sort of carefully capture the impact of the learning rate in this accuracy of the policy evaluation. Okay. In particular, you can tolerate the higher amount of policy evaluation error if you're using a larger step size. And this right-hand side bound is sort of maximized when you take the largest policy, so largest learning rate. Okay, so with this in hand, you can essentially combine this result with any existing sample-based policy evaluation algorithm to achieve a sample complexity bound on using entropy regularized MPG method. Okay, so with the rest, maybe 3 or 4 minutes, I'm going to just give you a glimpse of the analysis. I'm going to basically just highlight 3 key things in our in sort of the analysis. Okay, the first thing I want to highlight is sort of a key lemma here. For people who know the literature in the analysis of policy, natural policy gradient descent, there's a key lemma which sort of monotonic guarantees the monotonic performance improvement of the value function, often known as a policy difference lemma. It turns out that there's a sort of a counterpart version for this entropy regularized problem, where we can capture the improvement of the policy using basically the KL divergence between your consecutive policy updates. Okay, so the implication of this policy improvement lemma is that essentially you can ensure when you run this NPG method, you can have monotonic improvement of your value function and the Q functions. Okay, now another important operator is a soft Bellman operator. So we know that the Bellman operator plays an important role in reinforcement learning and dynamic programming in guaranteeing the success of classical methods such as policy iteration and value iteration. There turns out a counterpart of Bellman operator that we call the soft Bellman operator, which is basically adapting the original one carefully with the contribution of the entropy regularization term. This operator inherits 2 key properties of the original Bellman operator. The first one is sort of the soft Bellman equation, where we know actually the optimal soft Q function is a unique fixed point of the soft Bellman operator. Okay. Another key property is that this soft Bellman operator also has this gamma contraction property in terms of infinity norm between distances of Q functions. So the distance of your Q function will contract by a factor of gamma when you apply the soft Bellman operator on them. So with these properties, you can actually immediately ensure the convergence of soft policy iteration when you use the largest possible step size, where the algorithm is basically a soft version of the policy iteration. So you can just duplicate the proof of policy iteration by swamping the Bellman operator by this soft version of it. Okay, now in the general case, when you use a general learning rate, you have to be a little bit more careful, but still the proof turns out to be no more than 2 pages. The key is to identify this very important 2x2 linear system based on the Lyapunov type of analysis in the following way. So I won't go into the details. If you're interested, you can read our paper. But sort of the key is we sort of figure out what is the key thing we need to check its errors through this vector xt, where say the first entry is basically the error in your Q function. In the second entry here, this has an additional term, which is this theta t. It's sort of auxiliary sequence. It is sort of proportional to the policy update, but a sort of unnormalized version of it. Okay. And the vector y is simply something depends on your initialization error. And with this, you can actually write out a linear system that checks the progress of the vector xt. And the key thing is this matrix A, which is a simple 2x2 matrix. It's a scalar matrix. It's actually also a rank 1 matrix where the non-zero eigenvalue is exactly 1 minus eta tau. Right? This is, if you remember, this is exactly the contraction factor we have for our entropy regularized algorithm. And now you see where it comes from. It's essentially from the spectrum of this matrix A. Okay. Okay, so with this, I'll conclude my discussion about entropy regularized IL. And as a conclusion for my talk, hopefully I was able to convey this key message about using preconditioning to accelerate the convergence, especially the computational efficiency of vanilla first order methods, even for very challenging non-convex problems. I think preconditioning is a classical idea to deal with yield conditioning in general in numerical optimization, but its value in understanding statistical non-convex estimation and machine learning is still largely unexplored. And I think there are many interesting, promising future directions that are worth exploring. I discussed 2 sort of case studies in this talk, but I think there's a lot more that we can explore in statistical learning, reinforcement learning, and many more. With that, I'll conclude. If you're interested in some of this paper, some of these talks, some of these works I mentioned in this talk, our papers are available on arXiv, as well as on my website. I want to thank the funding agencies who supported this work. Thank you so much for your attention. I'm happy to take any question you may have.
Thank you, Professor Shi, for the great talk. So let's look at the questions. And the first question is regarding on the 15th slide. And the question is, how do you calculate the matrix energy? And is it similar to PCA or SGD?
Is that the toy example I showed for the chlorine concentration level one? Sorry, it's just too many animations. Sorry, it's easier for me to move the slides now. Yeah, so basically, exactly, this is just compute the SVD because this matrix is actually fully known. We just compute the SVD of this matrix, and you can compute the energy level just by computing the ratio of the sum, the singular value you are keeping, and the total sum of the singular values.
Thank you. And And the next question is regarding the comparison between scaled SGD and vanilla SGD. So the question is how do they compare in terms of the amount of computation, and does it so does the scaled GD also achieves a smaller error when they have the same amount of computation resource?
Yeah, that's a very good question. I think the question is about the sort of the in the figure I showed. I'm plotting the x-axis as iteration count because I want to highlight the fact that sort of scale GD, if you look at iteration count, it sort of aligns with the one of vanilla GD with perfect conditioning. But if you plot the x-axis as runtime, for example, the scale GD will sort of toward the right, just a little bit. We actually have those figures, but I didn't show it here. It still compares favorably, actually a lot favorably to the yield condition problems. You'll be a little bit worse than vanilla GD if you have perfect conditioning, right? That's for sure. But in general, if, you don't expect the condition number to be exactly 1, and you still have computational advantage.
Thank you. And the next question is it possible to extend this result from GD to other gradient-based algorithms such as momentum?
That's a great question. I think it's very interesting to explore. I don't know the answer. I think it's a very interesting question to explore.
Okay, thank you. And another question actually raised by 2 attendees is that, is it possible to further, could you please further elaborate more on the intuition of the preconditioner for this scale GD?
Yeah, sure. Yeah, I think I see a question about the preconditioning, about whether it relates to the block diagonal, the Hessian. Yeah. It's actually very onto the point. Basically, if you think about the population version of this problem, just think about matrix factorization. Then that basically gives you the exactly diagonal approximation of the Hessian for the population problem. Yeah, so that is actually our kind of original motivation. There are different ways to motivate this sort of preconditioning. In the paper, we elaborated a lot more. We try to explain it from different angles. So using the connection to sort of the diagonal approximation of Hessian is actually another interpretation we used. And in the talk, I try to sort of highlight this invariance property because I think the reason that vanilla GD is sensitive to unbalancedness of the factors and sensitive to the condition number, really because it does not have this important invariance properties.
Mm-hmm. Thank you. And the following questions are regarding the second part of your talk. And the first question is in terms of convergence of policy optimization, policy gradient. So is it possible to, you demonstrated that the vanilla natural gradient, a natural policy gradient converges sublinearly, but the entropy regularized MPG converges linearly. So I was wondering if it's possible to use regularized MPG as a warm start, and because when you add regularization, you add a small bias. Is it possible to first run the regularized MPG and then use the solution as an initial point for vanilla MPG?
Yeah, that's a good point. So in the paper, we actually also discussed this. So you can set the, let's say you have a target accuracy for solving the unregularized problem, say epsilon, right? You can actually set the entropy regularizer tau proportional to epsilon, and then solve the regularized problem to a corresponding, say, epsilon accuracy. And in that way, you also get a sort of a epsilon optimal or 2 epsilon optimal solution to the unregularized problem. So it turns out just by doing that, our iteration complexity is actually also better than just running the vanilla MPG method on the unregularized problem. but we are not sure whether it is sort of decisive argument because we are only comparing upper bounds of these iteration complexities. We don't have a corresponding lower bound to say it is really better.
Thank you. And another question is raised by Kai Liu, and the question is does adding the regularization term makes the geometry landscape an epsilon strong convex, so the condition number will decrease, is decreased by this regularization term?
Yeah, it does. I mean, if you look at the current slide, right, it does sort of mimic the story when you compare convex optimization versus, optimizing convex function versus optimizing strongly convex function by adding regularization. But the key is we are not dealing with convex problems. The landscape is still non-convex. So you don't really have a, you don't get strong convexity by adding regularization. And that is sort of the key of this work is, despite the non-convexity, you still see this type of acceleration with entropy regularization.
Thank you so much. And maybe the last question. So it might be a bit off topic. So regarding your example of the 3-arm bandit, I was wondering if you have some intuitive explanation of the geometry of the policy gradient method. It seems that there are a few sharp turns of the trajectory, especially on the top of the upper part of the figure. It seems the policy gradient seems to behave badly for a long time, and suddenly it learns how to go to the.
Yeah, I think what happens, I don't recall exactly how the example is sort of cooked up, but my intuition is that because of maybe the way you initialize the policy, is may first follow a wrong trajectory to sort of go to the wrong arm. For example, in this toy example, you have another arm which is suboptimal but close to being optimal, right? It's 0.9 thing. So it kind of sort of misleads there, and then sort of eventually sort of getting out of there and go to the right one. So that's sort of why it has this sort of trajectory. It kind of has to visit the other suboptimal ones before it gets to the optimal one.
Thank you. So, by the way, how do you collect the data in this toy example?
Well, this toy example is using the exact gradient. This is showing the gradient flow using exact gradient.
Oh, I see. So there's no sampling involved.
No. So this is like the one where we assume you have exact model, right? And then later you can do inexact versions, which will just be noisy versions of this. Yeah, these pictures are shown using exact gradient.
Thank you. So that concludes all the questions, and thank you so much for this wonderful talk.
Thank you so much for having me.
Thank you, and also thanks everyone for joining today, and we look forward to seeing you next week.
Okay, great. Thanks. Bye.
Thank you. Bye. Bye.